In this video, I'll show you how to solve the ALEKS problem called Solving Combustion Thermochemistry Problems. This particular ALEKS problem has 3 different versions, and in this video, I'm going to be showing you how to solve the version of the problem that is asking you to calculate the number of canisters you need for a wilderness expedition. If you are looking for the version of the problem that's asking you to do some calculations on a molecule that's being burned in a calorimeter, then please look for my video called Solving Combustion Thermochemistry Problems Part 1. That's where you're going to find the tutorial for that problem. And if you are solving this problem and you've got a data table that looks like this, then look for my video Solving Combustion Thermochemistry Problems Part 3. That's where I'm going to go over how to solve that particular problem. So in this version of the problem, you are being given a particular type of fuel. For my problem, I've been given C3H8, but this is not the same molecule that is used in all of the examples of this problem. For example, you might have C4H10. First thing that you need to do is write a balanced equation for the molecule that you have been provided undergoing a combustion reaction. So that's going to be your molecule, whatever it is, mine is C3H8, reacting with O2 because it's a combustion reaction, and the products of a combustion reaction are CO2 and H2O. So again, you're going to take whatever molecule you have and you're going to react it with O2. The products are CO2 and H2O, and you need to balance this equation. So I'm going to try to do that pretty quickly here. I've got 3 carbons on each side. I've got 8 hydrogen and 10 oxygen. 6 plus 4 is 10. It is really important that you get this equation written and balanced correctly. You are absolutely going to get the problem wrong if your equation has not been balanced correctly. So this problem is asking us to determine how much fuel we need in order to boil a certain amount of water. And what we are going to do is figure out how much energy is needed to boil the specified amount of water. And we're also simultaneously going to be figuring out how much energy is given off every time this particular reaction takes place. Let's start with that calculation. So let's begin by determining how much heat is given off every time this reaction occurs. To do that, we're going to be calculating the enthalpy of this particular reaction, the enthalpy of reaction. And we're going to do that using Hess's law, which says to calculate the enthalpy of reaction, we're going to use the enthalpy of formation for all of our reactants and products. We're going to calculate the enthalpy of formation for all of our products, and then from that number, we're going to subtract the enthalpy of formation for our reactants. So the equation for using Hess's law to do this calculation looks something like this. The sum of the enthalpy of formation for all of the products, and each one of them gets multiplied by their stoichiometric coefficient, minus the sum of the enthalpy of formation of all of the reactants. And so what I have done is I looked up the enthalpy of formation for the CO2, the H2O, and the O2. I've got that copied down there. I took that out of ALEKS's data tab. And then the problem is actually giving us the enthalpy of formation for the propane, C3H8 is right there. So that's the data that we're going to use to do this particular calculation. For our products, doing this calculation, we're going to start with our products. We're going to take each product, multiply by the stoichiometric coefficient, the enthalpy of formation of each one of the products. So we've got 3 CO2 molecules. That means we're going to go 3 times the enthalpy of formation of CO2. And then we're going to add to that our H2O. There's 4 H2O molecules, so 4 times the enthalpy of formation for H2O. That's going to give us the enthalpy of formation for all of our products. And then from that, we're going to subtract the enthalpy of formation for all of our reactants. First, we have our C3H8. There's only one of them, C3H8. And then our other reactant, we have 5 of those O2 molecules. So 5 times the enthalpy of formation for O2. And now we can go ahead and plug in the numbers for all of these enthalpy of formation values. So we've got 3 times the enthalpy of formation of CO2, which is one of the numbers that I looked up in ALEKS's data tab. That's negative 393.5. I'm going to leave the units off just to kind of save space, but we've got the units right here to remind us what they are. For our H2O, and this is H2O gas, negative 241.8 kilojoules per mole. And then for our reactants, the enthalpy of formation of C3H8, remember that was provided to us in the problem. There's only one stoichiometric coefficient of 1, so there's only 1 here, times negative 103.8 kilojoules per mole. And then the enthalpy of formation for O2, that is a 0, so I'm just going to drop that whole term off. And then let's just continue carrying out the math here. 3 times negative 393.5 plus 4 times negative 241.8 minus a negative 103.8. This is going to give us the enthalpy of the reaction, negative 2043.9. I'm going to bring those units back, kilojoules per mole. So again, what we've done is calculated this is the amount of energy that is released every time this particular reaction takes place. And the problem is asking us, again, let's go back to what the problem is asking. The problem is asking us to figure out how much of this fuel we're going to need to heat a specific quantity of water. So we have figured out how much energy is produced every time this reaction occurs. Now what we need to figure out is what is our energy need? How much energy are we actually going to need? So this problem tells us that we're going to be gone for 12 days and we're going to heat 3 kilograms of water each day. So that means that we're going to need a total of 36 kilograms of water. And I'm just going to convert that straight into grams, 3,600 grams of water. That's how much we are going to need to heat. And it tells us that we're going to be heating it to the boiling point, which is 100 degrees Celsius for water. And it tells us to just assume that the water is going to be 25 degrees C. So that means that we are heating our water from 25 degrees up to 100 degrees. So that is a change in temperature of 75 degrees. We've got to raise that water by 75 degrees. To figure out how much energy we need, what we're being asked to calculate is how much energy is it going to take to raise the temperature of 3,600 grams of water. I realize that I just did my math wrong there. That would have been a bummer. 36 times 1,000 is 36,000. Okay, so the question is asking us how much energy do we need to raise the temperature of 36,000 grams of water by 75 degrees Celsius. And the way that we're going to do that calculation is using the Q-SMAT equation. This equation is going to tell us the amount of heat that is necessary to raise a specific amount of an object by a particular change in temperature. In this equation, S is the constant, the specific heat capacity. For water, the value of S is 4.184. Those units are joules per gram degrees Celsius. The mass of the water that we're working with is that 36 kilograms or 36,000 grams. And that temperature change that we're looking for, again, is 75 degrees Celsius. That is changing the temperature from 25 up to the boiling point. Your problem may not be starting with 25, but you're going to be able to calculate your own delta T based on what your starting temperature is, the boiling point of water being 100 degrees C. So again, this is telling us the total amount of heat that we're going to need for all of this water. 4.184 times 36,000 times 75. We need 11296,800 joules. Take a look at how our units are going to cancel out here. We're going to be left with units of joules. Now over here, when we did this enthalpy calculation, we were in units of kilojoules. So let's go ahead and convert this into kilojoules. By dividing it by 1,000, 11296.8 kilojoules. And I'm going to do that on the calculator also, just so that we have that number in the calculator in case we need it. Okay, so this is the amount of heat that is needed to heat up all that water. And this is the amount of heat that is produced every single time this reaction runs. Now, another way that I want you to think about this number right here, because depending on which fuel you're using, if you don't have C3H8, this part might be a little bit more tricky. So this 2,403.9 that I have for my problem, kilojoules, is kilojoules per mole, specifically per 1 mole of C3H8. And this 1 that I'm getting in this particular way to write this particular way that I'm choosing to express this number, this 1 that I'm getting is the stoichiometric coefficient from this balanced equation. So let's just pretend, even though it's not right, let's pretend like when I balance this equation, I got a 2 there. Then in this equation right here, I would want to put a 2 here for every 2 moles of my fuel, because that's the stoichiometric coefficient for my fuel in this particular combustion reaction. I do know that some of these problems have C4H10 as the fuel. When you balance that equation, you are going to get a stoichiometric coefficient of 2 for C4H10, which means you are going to need to put a 2 down here in order for this problem to work out. Okay, let's get rid of all that. So this is the amount of heat that is evolved for every 1 mole of C3H8 that I burn, and this is the amount of heat that I actually need. And the question is asking, how much fuel am I going to need to produce this heat? So here's what we're going to do next. We're going to take the amount of heat that we need, 11296.8 kilojoules, and we are going to divide it by the amount of heat that's given off every time this reaction runs, 2043.9 kilojoules per mole. And when we do the math on this, actually let me bring that kilojoules per mole of propane back, mole of C3H8. And when we carry out the math on this, 2043.9, this is going to tell us how many moles, 5.527 moles of fuel, C3H8, that I need in order to heat up all of this water by that specific amount of temperature. So again, I took the amount of heat that I need in order to heat up all of that water, and I took the amount of heat that is produced every time the reaction runs, not forgetting to include my stoichiometric coefficient of my fuel, did the math, the kilojoules are going to cancel out, and this tells me how many moles of C3H8 I need. Now the problem is asking me to express the answer in terms of canisters, and in here somewhere it tells me the capacity of the canister in terms of grams. So what I want to do is take this moles of C3H8, and I'm going to convert that into grams of C3H8 using the molecular weight of C3H8, which I looked up before I started solving the problem. 1 mole is 44.097 grams. So this is going to tell us how many grams we need. 44.097, 243.7 grams. And now, next thing that we're going to do is it's going to tell us, because again, the problem wants us to answer in terms of canisters. Each canister is 75 grams. So we're going to take this number and we're going to divide it by 75 grams per canister. And I'm really running out of room here, so I'm going to have to squeeze my answer up here. 243 divided by whatever your capacity of your canister is, because for the problems, ALEKS does vary the capacity of the canisters. I get 3.25 canisters. Now, it wants us to round to the whole canister, not 3.25. If we only take 3 canisters, it's not going to be enough because we need a little bit more than 3. So for this particular problem, I'm going to need at least 4 canisters. This is a reasonable number for this problem. So when you're solving this problem, expect to see, I solved this problem maybe about 4 or 5 times, and every answer that I got here was like 2, 3, 4, 5, some relatively small number. You shouldn't be getting anything massive. This is a really tricky problem. There's a lot of calculations that need to be done. This part right here, making sure to include the stoichiometric coefficient of C3H8 or whatever your fuel is, don't forget that. I didn't really talk at all about, I just kind of dropped the negative sign off of this, and that is Hopefully you're comfortable with that, but that has to do with the difference in heat flow between these two systems. So this reaction is giving off heat, this reaction is absorbing heat. The heat is the same in terms of quantity, but it's different in terms of the sign because one of the reactions is losing the heat, the other process is gaining the heat. The value of the sign is not so much important. Again, I can't emphasize enough, make sure your equation is balanced, because if these numbers in this particular calculation are wrong, then this number is going to be wrong. And when you plug it in down here, this number is going to be wrong and the whole thing is going to go wrong. Be patient with yourself while you're working on this problem because it is really tricky.